Let's look at identifying whether a linear, quadratic, or exponential model best describes the data. So for example, we will determine whether the given function is linear, quadratic, exponential, or none of these. And then we will find the model. So here's my table of data. I have x values and y values. X values go from -1 up to 3. Y values go from 5 to -7. And first we're going to look at using the method of finite differences and or common ratios. So first, calculate the average rate of change of y with respect to x. In other words, let's find the first differences. So going from our first row to our second row, we will look at the change in y over the change in x. So 2 minus 5 over 0 minus -1, which is -3. And then from our second row to our third row, our change in y over change in x is -1 minus 2 over 1 minus 0, which is -3. And then my next comparison, we have -4 minus -1 over 2 minus 1, which is -3. And our final comparison, -7 minus -4 over 3 minus 2, which is -3. Now, our x values do go up by ones, so I could have just looked at the difference between the y values, so 2 minus 5, and so on, -1 minus 2, and that would have got us our -3s as well. So number 2, if the average rate of change, the first differences, is constant, like it is here, the function is linear. And then the average rate of change, or the first difference, is the slope. So m is -3. And we see in the table, we have 0 as an x value and y is 2. That means my y-intercept is 2. And if we're determining our linear equation, y equals mx plus b, substituting in these values, we get y equals -3x plus 2. And that would be our linear model. Okay, let's look at a second table of data. Let's start by calculating our average rate of change, or first differences again. So going from our first row to our second row, we have 16 minus 32 over 0 minus -1, and that is -16. Going from our second row to our third row, we have 8 minus 16 over 1 minus 0, and that is -8. Going from our third row to our fourth row, we have 4 minus 8 over 2 minus 1, and that is -4. And then our final comparison, we have 2 minus 4 over 3 minus 2, which is -2. Again, our x values went up by ones. But here, we do not have a constant first difference. So this is not linear. So let's try calculating the ratio of consecutive outputs. So we'll look at 32 and then 16. So our ratio of our consecutive outputs would be 16 over 32, which is 1/2. And then the 16 and 8 over 16 is 1/2. 4 over 8, which is 1/2. And 2 over 4, which is also 1/2. So here we have a common ratio. These ratios are constant, then the function is exponential. And this the ratio of consecutive outputs is the growth factor, which is our b in our exponential model. And then in our table, we can see that when x equals 0, y equals 16. So our a in our exponential model will be 16. Our exponential model has the form y equals a times b to the x. Let's substitute in what we now know. So y equals 16 times 1/2 to the x power. That is our exponential model. Here we have a third table of data. Okay, let's calculate the average rate of change, or the first differences. And we get 4 minus 2 over 0 minus -1, which is 2. And then 7 minus 4 over 1 minus 0, which is 3. And then 11 minus 7 over 2 minus 1, which is 4. And 16 minus 11 over 3 minus 2, which is 5. These are not the same, so this is not linear. Now let's calculate the ratio of consecutive outputs. Okay, we've got 4 over 2, which is 2. 7 over 4, which is 7/4, and then 11 over 7, and then 16 over 11. These are all different, so this is not exponential. Okay, let's calculate the second differences. So going back to our first differences, which were 2, 3, 4, and 5. So going from 2 to 3, we have 3 minus 2 over 1, which is 1. And then we have 4 minus 3 over 1, which is 1. And then 5 minus 4 over 1, which is 1. So our second differences are all the same, and they're all 1s. And these are constants, so this is quadratic. So a quadratic model has the form y equals ax squared plus bx plus c. And a will be the second difference, in our case 1 divided by 2. C is the y-intercept. And we will use x and y values to find our b. And we'll get the x and y values from the table. So a is 1/2, our first difference, over 2, so 1 over 2. Our y-intercept from our table is 4. That's my c. We don't know b yet. I'm going to choose an x and y value for my table. I'm going to choose 1 for my x, which means 7 is my y. And now I will substitute into the model. So y, 7, equals 1/2 times 1 squared plus b times 1 plus 4. Or 7 equals 1/2 plus b plus 4. Or 7 equals 9/2 plus b. I'll subtract 9/2 from both sides, and I get b is 5/2. So our quadratic model is y equals 1/2 x squared plus 5/2 x plus 4. Now, the work to calculate this is not always this simple. It might require a system of equations if we did not have the y-intercept. Okay, I also want to point out that we could look at graphing our table of data to get a feel for whether our data could be represented best by a linear, quadratic, or exponential model. So here is our first table that we looked at a moment ago. If we plotted these points, I have -1, 5, 0, 2, 1, -1, 2, -4, 3, -7, and these points fall in a line. We did find that a linear model was best, and our graph does verify that. So this was linear. This is our second table again. So let's plot these points. I'm going to change my scale on my y-axis so that every line is worth 5. But my x-axis, my scale is still going to be 1. So I have negative 132, 0, 16, 1, 6, 2, 4, 3, 2. And this does look exponential, and that is what we found when we were looking at that. We found a common ratio. And then our last table that we just looked at, if we plot these points, so negative 1, 2, 0, 4, 1, 7, 2, 11, 3, 16. Okay, it's not conclusive, but it looks like this could be part of a parabola. We did find that this had a constant second difference, which meant that this is a quadratic. But again, graphing will give us a feel for what model might be best, but it won't be conclusive.